Identify the set of values x for which y will be a real number. This is another way of asking what's the domain of the problem. We know that x plus 7 down in the denominator is not allowed to equal 0, and therefore x is not allowed to be negative 7. So the domain is going to be the set of all values x such that x is not equal to negative 7. In this next problem, we need to make sure that what is under the radical is non-negative. I write it this way because this is a word we don't use very often. It means not a negative, but allowing it to be either equal to or greater than. So we want to make sure that x minus 10 is greater than or equal to 0, and therefore that x is greater than or equal to 10. In set builder notation, this is the set of all x's such that x is greater than or equal to 10. We are asked to graph this next equation by plotting points. Notice how y is squared, and that's not something we usually have. I'm going to write this as y squared plus 1 equals x so that we can isolate the x, and it asks us to plot points, so I'm going to set up an xy chart. But it's easier on this problem to substitute in values of y as the input to get x coming out. So if I let y be 0, we get 0 squared plus 1, which is 1 for x. And if y is either plus or minus 1, both of them when squared make 1, plus 1 makes 2. And both plus or minus 2 when squared makes 4, plus 1 gives us 5. And so we've just in a compact way actually found 5 points. Now 1, 0 is to the right of the origin. We're going to plot 2, 1 and 2, negative 1, as well as 5, 2 and 5, negative 2. And then we are going to draw the curve, which you can tell is a sideways parabola, through these points. The question is now, is this a function? And the answer is no, this is not a function. Why is it not a function? It violates the vertical line test. When something is not a function, it is called a relation instead. X and y are in a relationship, but it's not that of a function where each x has a unique y value that goes along with it. This next problem asks us to identify the x and y-intercepts, and to me this is a little too easier for this course. Notice the y-intercepts are at plus and minus 3, so let's start with that. Y-intercepts, that would be 0, 3 and 0, negative 3, always writing them as a coordinate point. And for the x-intercepts, we can see at the left we have one at negative 1, and at the right we have one at 9. So negative 1, 0 and 9, 0 will be those x and y-intercepts. If we don't have a graph and we have an equation, we can find the x and y-intercepts more easily by substituting x and y equals 0 into that equation. Let's go with the old xy chart and let x be 0. When you substitute 0 into this equation, it's like crossing out that negative 3x, and all we have left there is negative 5y equals 60. Therefore, y will equal negative 12. And that tells us that the y-intercept is at 0, negative 12. Now if we let y equals 0, going up to our equation here, that zeroes out that part of the equation. We now have left negative 3x equals 60, and dividing each side by negative 3 gives us negative 20. And that tells us the x-intercept will be at negative 20, 0. Whether we're dealing with lines, parabolas, circles, absolute values, it doesn't matter. The rule of substituting in 0 for x to get the y-intercept and substituting in 0 for y to get the x-intercept will always work. Always.